All right, let's dive right into this explainer. Today, we are exploring the absolute backbone of modern data architecture, and that is Apache Kafka. We're going to trace its mechanics all the way from fundamental event streaming concepts right up to the massive enterprise-grade data pipelines that handle literally millions of events per second.
But before we get into the weeds, let's establish a quick baseline here. Who, or I guess more accurately, what is Kafka?
Now, if you're a big fan of classic literature, your mind might immediately jump to Franz Kafka, the 20th century author famous for deep existential dread and agonizing insomnia. But don't worry, we are focusing on Apache Kafka today. So absolutely no existential dread here, just a highly scalable, distributed event streaming platform that is purpose-built for incredible throughput and fault tolerance.
Here is our game plan for today. We're going to cover the pub-sub paradigm, the anatomy of a topic, scaling with consumer groups, surviving system failures, and finally, the magic of exactly once processing.
Okay, starting with Section 1, the pub-sub paradigm. Let's look at the fundamental architecture.
Imagine a traditional software setup. You've got services talking directly to each other, right? It creates this really fragile, tangled web. If one single service goes down, the whole workflow can just cascade into a massive failure. Well, a topic-based publish-subscribe system solves this through what we call temporal and referential decoupling. Basically, publishers just send their messages to a central middleware broker, and then subscribers pull whatever they need whenever they need it. They literally don't even need to know the other exists, which completely eliminates that tight coupling. So, to put a formal definition on it, Apache Kafka is a distributed event streaming platform. I always like to think of it as a giant, highly efficient digital post office. Producers drop their events into specific mailboxes, the Kafka cluster stores them incredibly safely, and then consumers come and pick them up. It combines publishing, storing, and processing all into one remarkably robust system. Moving on to Section 2, Anatomy of a Topic. Let's see where these events actually live.
So, a topic in Kafka isn't just one giant endless bucket. It's actually broken down into smaller parallel partitions. And this is key because these partitions are spread out across multiple different brokers, which allows Kafka to scale horizontally. Because it's split up like this, multiple consumers can read from different partitions at the exact same time, which just drastically increases your overall throughput.
But within those individual partitions, the ground rules are actually super strict. Messages are append-only and completely immutable. That means once a message is written, there is no going back to change it, period. And to keep track of this massive flow of data, every single message gets an offset. It's basically a unique sequential ID number, kind of like a digital bookmark, that consumers use to track exactly where they left off in the log. This is what makes reliable recovery and message replay possible.
All right, Section 3, Scaling with consumer groups, how we share the load.
This right here is where the magic of load balancing happens. See, a single consumer trying to process everything will very quickly become a bottleneck. So Kafka uses a consumer group to divide the labor. Multiple consumers team up and share the partitions. And Kafka acts like a traffic cop here, ensuring each partition is exclusively owned by only one consumer within that group at a time. The best part? If one of those consumers crashes, the others instantly detect it and redistribute the load. It's a completely self-healing division of labor.
Which brings us nicely to Section 4. Surviving system failures, handling network drops and crashes.
Let's face it, hardware fails. To survive that, Kafka relies heavily on replication. For any given partition, one broker is appointed as the leader, and it handles all the active read and write requests. But in the background, you have follower brokers constantly copying that exact data. If a broker physically goes up in smoke, a follower that has a perfect, up-to-date copy just seamlessly steps up to become the new leader. Bam! No data loss, and high availability is maintained. But there's another sneaky failure scenario we have to talk about. What happens if a producer sends a message, but then a random network timeout happens right before it gets the confirmation? Well, the producer is going to do what it's supposed to do, retry. But traditionally, that retry creates a duplicate message in the system. Kafka solves this headache with the idempotent producer. It basically attaches a tiny sequence number to every single message. If the broker sees the same sequence number pop up twice, it just silently tosses the duplicate in the trash. It survives those network retries effortlessly, and it does it without the heavy performance hit of cross-partition coordination. Finally, Section 5. The magic of exactly once. The holy grail of distributed systems.
For the longest time, engineers just had to deal with the messy reality of at least once delivery.
Sure, your data was safe, but all those network retries meant you might end up processing a user's payment or order multiple times. You had to write all this custom, complex deduplication code to fix it. But Kafka's exactly wants semantics guarantee atomic multi-partition writes. Simply put, absolutely no data is ever lost, and you will absolutely never see a duplicate.
This is a massive deal for streaming applications that rely on the read, process, write cycle. Think about it. You read an event, you transform that data, and you write the result. The nightmare here is the dual write problem, writing your output to a new topic while simultaneously committing your offset marker to prove you finished the job. Kafka Brilliant solves this by grouping these actions into a single atomic operation. That means they either completely succeed together or they completely fail together. There is no messy in between.
So how does Kafka actually pull this off under the hood? Well, this atomic operation relies on Kafka's transactional API. A transaction coordinator manages the whole lifecycle using a clever two-phase commit protocol. It pushes these little transaction markers directly into the data log. Because of this, the downstream consumers only ever see messages from fully 100% completed transactions. If the system crashes mid-process, the transaction just cleanly aborts itself like it never even happened.
And guys, this was a total game changer for the industry. As Neha Narkade, one of the co-creators of Kafka, put it, this is a lightweight transaction protocol specifically designed for streaming data workflows. In the past, traditional distributed database transactions required these heavy, painfully slow locking mechanisms that just absolutely destroyed system performance. But Kafka somehow achieved exactly one's semantics without sacrificing that blazing, high-throughput speed it's so famous for.
So, what's the big takeaway here? Why does all this matter? Because out in the real world, resilience is not just a nice-to-have, it's absolutely mandatory. When you are processing billions of financial payments, tracking entire fleets of IoT sensors, monitoring real-time cybersecurity threats, or handling crazy volumes of e-commerce orders, you cannot afford to drop a message, and you definitely cannot afford to process a payment twice. Entire industries rely completely on these fault-tolerant pipelines to keep the modern world functioning every single day.
The reality is, networks are going to drop and servers are going to fail. It is completely inevitable. So the question I'll leave you with is this. How will you implement these exactly one's pipelines in your own architecture to survive the chaos? I really hope this explainer has empowered you with the concepts to go out and build something incredibly resilient. Thanks for hanging out and learning with me today, and keep building.